Hello, today we're going to talk about the chi-square goodness of fit test. So far we have learned about hypothesis testing whenever we want to test claims based on population means, which is the student's t-test or the two-sample t-test. However, if we want to make claims about a population's proportion, then we have to use the chi-square goodness of fit test. So just like with the t-test, we have our null and our alternative hypothesis. So the null hypothesis is basically saying that nothing is changing, that the data is going to fit the description that is given, or that is thought to be in place. The alternative hypothesis is that the data is not going to fit the description that is stated. So next, we have what we call degrees of freedom. Your degrees of freedom can be found by taking the number of categories and subtracting one from it. So the steps to success to conduct a chi-square goodness of fit test successfully is very similar to the t-test. So the first thing that you want to do is you want to state the null and alternative hypothesis, and then you want to identify or choose your significance level, which we denote as the Greek letter alpha. And then we want to calculate or identify the test statistic, which we also call the chi-square calculation, or we can call it the chi-square stat or chi-square statistic. Making sure that you understand in the chi-square calculation formula, which is the sum of the squares of the differences between the observed and the expected frequencies divided by the expected frequency. We are going to add each of those up. Remember that F sub 0 is your observed frequency, F sub E is your expected frequency. Once we calculate our test statistic, we are then going to use the calculator to find the p-value, which is denoted as p. And then we are going to use the critical value chart to find the critical value. And I'm going to show you how to use that below in 1 second. And then we need to finally accept or reject the null hypothesis. We are going to reject the null hypothesis if our p-value is less than the significance level, just like when we did the t-test. And we can also add in that if your chi-square statistic is greater than your critical value, then you also need to reject the null hypothesis. No matter which evidence you use, you should come to the same conclusion. Okay? Next, the opposite of rejecting the null hypothesis is to accept the null hypothesis. So we are going to accept the null hypothesis anytime the p-value is greater than the significance level, or this test statistic is less than the critical value. So that is when we are going to accept it. So last but not least, once we decide whether we are going to reject or accept it, we are then going to state the conclusion and interpret it in the context of the situation. So in terms of reading a critical value chart properly, in order to find the critical value, it is going to be based upon two things. It is going to be based upon your significance level, and it's also going to be based upon your degrees of freedom. So for instance, if I wanted to find the critical value for my chi-square statistic that I'll be comparing to for a significance level of 5% and a degree of freedom of 4, I would literally line my significance level of 5%, which is 0.05, and I would line up the degrees of freedom, and where they cross would be my critical value here, which is 9.488. Okay, so that's just an example on how to read the critical value chart. So now let's look at example number 1. So for example number 1, it states that Kamari thinks that students at his college are equally likely to study any of the 4 mathematics courses. He asks a random sample of 80 students and obtains the following results. So the results here, we have 4 math courses and we have the number of students in each course. It is saying here that Kamari is going to conduct a chi-square test using a 2.5% significance level. We need to state the null and alternative hypothesis. So my null hypothesis is that every student is going to be equally likely to study any of those 4 courses. All right. My alternative hypothesis is going to be that the students are not going to be equally likely to study any of those courses. So next, we have to calculate the expected frequencies. What do we expect to happen? Well, if it says that we are talking about being equally likely to study any of those four courses, that means that there needs to be the same amount of students in each course. So we know that we have a 25% chance, and if we take 25% of 80.25 times 80, we would get 20. So that lets me know that each of my expected frequencies should be 20 in each one of those boxes. So now for part C, we have to calculate the test statistic. So in order to calculate the test statistic, what we have to do is we have to take each observed frequency and subtract the expected frequency, then square that difference, and then divide by the expected frequency, and then keep doing that. And you're going to add up all of those chi-square calculations to get the sum of them. So in order to do that, I would literally have to take 24, subtract 20, square that, and then divide it by 20. And then I would have to add it to 11 minus 20 squared divided by 20. Then I would add 36 minus 20 squared divided by 20. And last but not least, I would add 21 minus 20 squared divided by 20. Once I do that, then I will literally type this into the calculator, and I will type in 24 minus 20 squared divided by 20 plus 11 minus 20 squared divided by 20 plus 36 minus 20 squared divided by 20 plus 21 minus 20 squared divided by 20. And when I do that, I end up getting 177 over 10. And then if I change this to a decimal by pressing math and then going to number 2 decimal, I end up getting 17.7 approximately. That is my chi-square statistic there. So now that I have my chi-square statistic, I can now calculate or state the degrees of freedom. So remember, your degrees of freedom is the number of categories you have, subtract 1. So I have 4 categories, 4 classes, and I'm going to subtract 1, and 4 minus 1 is equal to 3. So 3 is my degree of freedom. Next, we are then going to use the calculator to find the p-value. So in order to find the p-value, what I am going to do is I'm going to run my test in the calculator. So I'm going to press stat and then edit. My observed frequencies are going to go in L1. And my expected frequencies are going to go in L2. All right. So now that I have those values in, I'm going to press stat and then go over to test. And then I'm going to scroll to the chi-square GOF test, goodness of fit. So when I scroll there, I'm going to make sure that my observed values came from L1, my expected frequencies came from L2, my degrees of freedom is 3, and then once I do that, I can calculate, and then I end up confirming that indeed 17.7 is my chi-square calculation or my chi-square statistic, and then I can see that my p-value is approximately 5.07 to the times 10 to the power negative 4, or I can just rewrite it as being 0.000507 in regular decimal form. So now that I have my p-value, then I want to use my critical value chart to find my critical value. So remember, in order to use your critical value chart, all you do is you take your significance level and you line it up with the degrees of freedom, and then you look at where they intersect, and that is your critical value. So If I go up here, we already know that we have a 2.5% significance level. So because we have that 2.5% significance level, what I'm going to do is I'm going to go up to 0.025 on the top, and then on the side, my degrees of freedom is 3. So I literally take my fingers and I trace and I match them up, and I will end up getting 9.348 on my critical value chart for that value. So next, we want to conduct the chi-square goodness and fit test to determine if Kamari was correct. Remember, it said in the question that Kamari feels like the students are equally likely to study one of those courses. So if we look at our p-value and our significance level, we will end up seeing that our p-value is less than the significance level, because 5.07 times 10 to the power negative 4 is actually smaller than 0.05 or 5%. And if we want to look at it from the standpoint of our chi-square calculation and our chi-square critical value, we will be able to see that our chi-square statistic or our chi-square calculation is greater than the critical value, because 17.1 is greater than 9.348. And from there, we know that we can say that there is sufficient evidence to reject the null hypothesis, and that means that Kamari is incorrect. Students are not equally likely to take those courses. So that is my solution there. So now let's look at example number 2. So let's look at example number 2 here. So example number 2 states that a theory predicts that 3 different types of flowers, A, B, and C, should appear in the ratio 1 to 2 to 3 respectively. That means one after the other in the same order. Next, it says that a sample of 60 flowers contains 17 flowers of type A, 21 flowers of type B, and 32 flowers of type C. The theory is tested at a 5% significance level. So the first thing that they want us to do is to state the null and alternative hypothesis. So we can say that our null hypothesis states that the flowers A, B, and C appear in the ratio 1 to 2 to 3, like it's stated. The alternative hypothesis is that the flowers will not appear in the ratio 1 to 2 to 3. So now we have to calculate our expected frequencies. So we already know that our observed frequencies are given to us in the problem. It says that we have 17 flowers of type A, 21 flowers of type B, 32 flowers of type C. So in order to see if we appear, or if the flowers appear in that ratio of 1 to 2 to 3, we have to understand what that means. That means that flower A should, in order to figure how many flowers B, how many type B flowers you should have, that's going to be double the amount of A. And the type C flowers are going to be triple the amount of A. So basically, I already should know that the number of flowers that I have of type A and the number of flowers that I have for type B and C should add together to give me 60 flowers total. Now, because I don't know how many of them I have, I'm going to say that the number of flowers of type A, I'm going to represent it as X. So based on the ratio, I will end up with the equation X plus 2X plus 3X is equal to 60. Because remember, the amount of type B flowers should be double the amount of type A flowers, and the amount of type C flowers should be triple the amount of type A. So now I'm going to solve this equation, and when I do that, I'm going to end up getting that 6x is equal to 60, and divide both sides by 6, I will end up getting that x is equal to 10. So if x is equal to 10, and x represents how many type A flowers that I will have 10 type A flowers. And then my type B flowers are double that, which is going to be 20. And then my type C flowers are triple the amount in type A, which is going to be 30. So now I can move on to part C, which is to calculate the test statistic. So what I'm going to do is I'm going to take the sum for each of these flowers, A, B, and C, of the differences of their, or the squares of their differences divided by the expected frequencies. So I'm going to start off by having 17 minus 10 squared divided by 10 plus 21 minus 20 divided by squared divided by 20 plus 32 minus 30 squared divided by 30. So once I have all of those, I'm going to type that into the calculator. So I'm going to end up having 17 minus 10 squared divided by 10 plus 21 minus 20 squared divided by 20 plus 32 minus 30 squared divided by 30. So once I put all that in the calculator, I'm going to press enter, and I end up getting 61 over 12, which as a decimal converts to approximately 5.08 and 3 significant figures. So that is my chi-square statistic, or my chi-square calculation. So next I want to calculate the degrees of freedom. So remember, your degree of freedom is going to be equal to the number of categories, subtract 1. So I have 3 categories, 3 flower types, subtract 1, that will end up giving me 2. So 2 is my degree of freedom. Next, I want to use the calculator to find the p-value. So I'm going to do that by going to Stat, Edit, and I'm going to put my data in. And I'm going to clear out any existing data in there. So I'm going to have 17, 21, 32. And then for my expected frequencies, I'm going to have 10, 20, and then 30. Once I have my data in, I'm going to press Stat, go over to Test, and I'm going to go to chi-square goodness of fit. And then I know that my observed frequencies are coming from L1. My expected frequencies are coming from L2. My degree of freedom is 2. And then I want to calculate my information. So as you can see here, my chi-square calculation or statistic is indeed 5.08. So I can use the calculator to calculate that. Remember, you don't have to calculate it by hand. I just showed it to you in case you forget how to use the calculator. And then we can see that our p-value is approximately 0.0787 and 3 sig fig. So now we want to use the critical value chart to find the critical value again. So we're going to focus on the 5% significance level and the 2 as far as the degrees of freedom. So I go up and I match up 0.05 with the degree of freedom of 2, and I end up seeing that my critical value is going to be 5.991. So now I want to conduct my chi-square goodness and fit test to determine if that theory is going to be correct. So when we look here, we will end up seeing that the p-value is greater than the significance level because 0.0787 is greater than 0.05. And then we can also tell by looking at the chi-square statistic and the critical value that the chi-square calculation or statistic is less than the critical value because 5.08 is less than 5.991. And from there, what we can decide is we can decide that there is not enough evidence to reject the null hypothesis. And that means that the flowers will not or don't appear in the ratio of 1 to 2 to 3, as it was stated or as the theory stated. Okay, so that is our second example. Now, there are some limitations here sometimes. So, in order for a chi-square test to be accurate, the sample size must be relatively large. We consider a sample size to be large enough if all of the expected frequencies are at least 5, meaning 5 or higher. Whenever we have expected frequencies of less than 5, we are to combine similar categories and then repeat the process um, of finding your chi-square calculation or statistic and comparing it with the critical value. We have to start that process all over again in order to get more accurate results. So for the example below, it says the tables below show the expected frequencies for an investigation on the amount of serious sports injuries treated by a hospital. Since the expected frequencies of 3 age groups are below 5, the data for those categories will end up being combined so that the expected frequency can be at least 5 or higher. So as you can see here, the age groups of 30 to 40, 40 to 50, and 50 plus are all below 5 individually. However, I know I just can't combine the 30 to 40 and the 40 to 50 age group because the 50 plus group will still have an expected frequency of less than 5. So I combined all three of them to give me a combined expected frequency of 5.5 by adding those together. So anytime you have expected frequencies below 5, you have to combine categories and then start your process over as far as finding your chi-square calculation or statistic and finding your critical value of the merged data. So if you have any questions on the chi-square goodness of fit test, please let me know and I will be more than happy to assist you. Have a great day.